Welcome to our comprehensive guide on augmented reality and virtual reality interview questions. Today, we'll explore the fundamental concepts of immersive technologies that every developer should master. From understanding the core differences between AR and VR to implementing advanced features in Unity and Unreal Engine, this series covers essential topics including spatial computing, user experience design, and performance optimization. Whether you're preparing for your first AR/VR role or advancing your career in immersive technology development, these concepts form the foundation of modern mixed reality applications. Let's start with the fundamental distinction between augmented reality and virtual reality. Augmented reality overlays digital information onto the real world, enhancing your perception of the physical environment around you. Think of Pokémon Go or Instagram filters. These applications add virtual elements to what you see through your smartphone camera or AR glasses. Virtual reality, on the other hand, creates completely immersive digital environments that replace the real world entirely. When you put on a VR headset like the Meta Quest or PlayStation VR, you're transported into a fully synthetic three-dimensional space where you can interact with virtual objects and environments. Understanding tracking systems is crucial for AR development. There are three primary approaches to AR tracking. Marker-based tracking uses predefined visual markers or QR codes that the camera can easily recognize and track for precise positioning of virtual objects. This method provides high accuracy, but requires specific markers to be present in the environment. Markerless tracking uses natural feature detection through SLAM algorithms. That's simultaneous localization and mapping, allowing AR applications to track surfaces and objects without predetermined markers. Location-based tracking combines GPS data with device sensors to create outdoor AR experiences, perfect for navigation apps and location-aware games. When choosing a development platform for AR/VR applications, Unity and Unreal Engine are the two leading options. Unity uses C# as its primary scripting language and excels in cross-platform deployment, making it easy to build applications for multiple devices from a single codebase. Unity's asset store provides thousands of ready-made components, and its strong AR/VR support through packages like AR Foundation makes it beginner-friendly. Unreal Engine offers blueprint visual scripting, allowing developers to create complex interactions without traditional coding. Unreal excels in high-fidelity graphics and comes with advanced VR templates, making it ideal for creating AAA-quality immersive experiences with stunning visual effects. AR Foundation is Unity's cross-platform framework for building augmented reality applications. The basic setup involves managing an AR session, which is the core component that handles the AR system lifecycle. In this example, we're using the Unity XR AR Foundation namespace to access AR functionality. The AR session component needs to be enabled to initialize the AR system and start tracking the device's position and orientation in the real world. This simple script demonstrates how to programmatically control the AR session, which is essential for managing when AR features are active in your application. The AR session is the foundation that enables all other AR features like plane detection, image tracking, and object placement. Spatial computing encompasses several key technologies that enable devices to understand and interact with three-dimensional space. SLAM, simultaneous localization and mapping, is fundamental to modern AR/VR systems. It creates real-time three-dimensional maps of the environment while simultaneously tracking the device's position within that space. 6 degrees of freedom tracking, or 6DOF, monitors both position along X, Y, and Z axes, as well as rotation including pitch, yaw, and roll movements. Occlusion handling ensures that virtual objects appear to hide behind real-world surfaces, creating realistic AR integration. Light estimation analyzes the real-world lighting conditions to match virtual object illumination and shadows, making digital content appear naturally integrated with the physical environment. User experience design in VR and AR requires special consideration for human comfort and natural interaction. Performance is critical. Maintaining 90 frames per second or higher prevents motion sickness and ensures smooth, comfortable experiences. Any frame rate drops can cause nausea and discomfort for users. Comfort design focuses on proper interpupillary distance settings and comfortable viewing distances to minimize visual fatigue during extended use sessions. Intuitive controls leverage spatial gestures and hand tracking, allowing users to interact with virtual objects using natural movements rather than complex button combinations. These principles ensure that immersive applications are not only functional, but also comfortable and enjoyable for extended periods of use. VR interaction systems rely heavily on hand tracking and controller input to create natural user experiences. Unity's XR Interaction Toolkit provides robust tools for implementing VR interactions. In this example, we're using an XR controller to detect grab gestures through grip input values. The controller's input device provides access to common usage features like grip pressure, which can be used to trigger grab actions when users squeeze the controller. The try-get feature value method attempts to read the grip value as a float, allowing for nuanced interaction where partial grips can be detected. This approach enables developers to create sophisticated interaction systems that respond naturally to user hand movements and gestures. Performance optimization is essential for maintaining smooth VR/AR experiences. Rendering optimizations include reducing polygon count in three-dimensional models, optimizing texture sizes to balance quality with performance, implementing occlusion culling to avoid rendering objects that aren't visible, and using level of detail systems that show simpler models at greater distances. System optimizations focus on object pooling to reuse game objects, instead of constantly creating and destroying them, minimizing garbage collection that can cause frame rate stutters, writing efficient update loops that don't waste processing power, and implementing spatial partitioning to only process objects that are relevant to the user's current view. Immersive technologies are transforming multiple industries with practical applications. In healthcare, VR enables surgical training simulations, patient therapy for conditions like PTSD and phobias, and medical visualization for complex procedures. Educational applications create interactive learning experiences that allow students to explore historical sites, conduct virtual science experiments, and attend virtual classrooms from anywhere in the world. Manufacturing industries use AR for assembly line training, allowing workers to see step-by-step instructions overlaid on equipment, and product design visualization to prototype and test designs before physical production. These applications demonstrate how AR and VR technologies are moving beyond entertainment to solve real-world problems and enhance human capabilities across diverse fields.
If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.